Sweet Mother Michigan, Father Superior, coming down from Mackinac and Sault Ste. Marie.
You have come upon the Great Lakes Guys podcast. We're just a couple of guys, Randy and Chris, who formed a podcast about all things Great Lakes. The podcast features not only the history, geography, and geology of the land, waters, and people of the Great Lakes Basin, but as well, we interview talented people from around the region who form the innovative cultural web of music, arts, technology, and science of the Great Lakes Basin. And before getting to the podcast interview, we would like to thank Lee Murdoch, the Great Lakes Balladeer, who allowed us to use his recording of the song, The Great Lakes Song. The Great Lakes Song was originally composed by Pat Daly, another prominent balladeer of the Great Lakes. Today's Great Lakes Guys podcast features Stephen E. Kesler, Professor Emeritus of the University of Michigan's Department of Earth and Environmental Sciences. Professor Kesler has written a book on the geological history of the Great Lakes Basin, appropriately entitled Great Lakes Rocks, 4 billion years of geologic history in the Great Lakes region. The book is published by the University of Michigan Press, 2019. If you want to understand how the Great Lakes region was formed and why it is the way it is, this is the book for you. The book is richly illustrated, which helps illuminate the sometimes complex and varied history of the region. Professor Kesler not only speaks with authority on the geological history of the region, but also on the associated history of the development of the abundant mineral resources of the region as well. In today's podcast, we take a sort of virtual geo road trip with Professor Kesler, where we will discuss locations within the Great Lakes Basin that reflect the mostly deep past of the region, from, say, approximately 2.8 billion years ago to something like 1 billion years ago. Thus, we will necessarily concentrate our attention to primarily the Upper Peninsula of Michigan, as well as associated regions in Minnesota and Ontario. Towards the end of the interview, we will speak somewhat about the copper and iron mining industry and some environmental aspects of that mining. We hope you will enjoy and learn from this interview with Professor Kesler.
Somebody said, let's go on a field trip to understand the Great Lakes region. I'd say, well, let's get in a car and we'd probably head up to the Upper Peninsula of Michigan for a start. I guess what we're going to try to do here is build ourselves a continent. Because as you know, when the Earth got started, there essentially, well, there wasn't anything really. This sounds almost biblical, but we didn't even have an ocean. The Earth had to cool a little bit, and then there was the Great Rain, and we got an ocean, and then we had to develop a continent. And it turns out that Michigan and the Upper Great Lakes region was a real part of that early process. We have in Michigan and adjacent areas over in Minnesota some of the very oldest rocks in the world, almost 4 billion years old. And these were part of that early continent building process. They're not particularly appealing rocks when you go up and stand on them. They don't thrill you. They don't show many patterns or anything. But you can stand there and just kind of sense, boy, this is really old. But if you go a little bit farther along in time, it's in the period of around 2.8 to 2.5 billion years where we really begin to see some rocks. And
can I interrupt? I'm sorry. So you're saying you stand on an ancient rock, and you know it's not remarkable maybe, but you know it's old. Why is that? Just because it's so featureless, or is it like you're standing on an asteroid or a comet, you know, at the birth of the solar system?
Well, these rocks have been through a hard time. They formed almost 4 billion years ago, and then they've gone through continental collisions and uplift and erosion and metamorphism and partial melting. And the form of the rock has changed so much that you can't really look at the rock and sense anything to do with near surface processes that might have formed them. And in fact, these so-called very old rocks that we have in Michigan are that old simply because they contain some very old minerals, particularly zircon, which is a zirconium silicate. And that's a very resistant mineral, and that just lasts forever. It never melts or anything. And so we can find those old minerals in these rocks, and we know this rock formed that long ago, at least that part of it did, but it's very hard to reconstruct exactly what its history was after it formed 4 billion years ago.
So where would I see these rocks in the Upper Peninsula? What's a fairly convenient location?
Outside Iron Mountain, you could see some, but the best place really to go is over in the Minnesota River Valley. In Minnesota. The entire river valley there contains these old rocks, and that's where they were first discovered over 50 years ago when we first learned how to use isotopic age measurements to determine the age of rocks. And at that time, they were truly the oldest rocks known in the world. Since then, we've found slightly older rocks farther to the north in the Canadian Shield, but that's where I'd go. But if you really want to see some rocks where you know, here's what happened, you're going to have to go a little bit younger, and that's where I'd go on my first field trip stop. I'd go to Marquette.
I see. Marquette, okay.
And I'd walk right along the shore, particularly south of downtown, and there you'll find exposures, and those exposures are what we call pillow lavas. They are pillow-shaped, bulbous masses of basalt lava. That's the kind of lava that forms Hawaii today. And that lava was extruded somewhere in the range of 2.7 to 2.5 billion years ago, when these older rocks that I mentioned a moment ago, they were floating around at the surface as small continents. But there was still a lot of ocean, and any magma or molten rock that came out usually came out underwater. And as a result of the quenching of that cold water that this hot magma came out in, it formed this pillow shape. And these are quite impressive rocks. You can see the pillow shape. You can sense that, by golly, that many billion years ago, this thing was coming up, trying to form an island in the middle of the ocean. If you go a little bit farther north of Marquette, you can find granitic type rock that is the magmas that came up and intruded into those basalt islands after they formed. And you have then in the Marquette region and slightly to the north, the pillow lavas that were the first stuff to form, and then the magmas of other material, granitic type material that came up and intruded those pillow basalts to make a continent that we can actually see and that hasn't been metamorphosed and deformed so much that you can't see your textures and features anymore. You can actually stand on that and you can see what was happening. So that's a great place to look at the very earliest rock that formed. And in fact, we didn't have very much in the way of continents. I mean, we had to have these little islands of continent collide in order to make larger and larger continents through time. The place I'd go to see the rocks I'm talking about is right along the shore in Marquette, and then up toward Presque Isle Park and along the coast up north from there.
Okay.
That's the best place to take a look at those things.
Okay.
Very good.
if you so here we've got ourselves a continent that's formed, and it was eroded, and a surface was formed on that continent, and sediments were deposited on that surface. And that happened starting around 2.4 billion years ago. And all along the north shore of Lake Huron, all the way through the Upper Peninsula of Michigan over into Minnesota, a sequence of sediments was deposited from about 2.4 billion up to about 1.8 billion years ago. And it's a very thick sequence of sediments. And there were some interruptions in it, but it turns out to be a very important sequence of sediments because among the sediments that were deposited, we had a important thickness of iron-rich rock that we now see in the Marquette area and in the Mesabi Range over in Minnesota. And these were what we call iron formations, which are rocks that are unusually rich in iron. They're very strange situations because somehow this stuff was being deposited in the ocean, but the ocean water shouldn't be dissolving iron. What happens when you put iron out? It rusts. Oxygen combines with the iron and you get rust. But somehow iron was dissolved in at least part of the ocean, possibly the deep ocean, and it was what we call upwelled, moved up into the shallow parts of the ocean, and it was deposited as this iron formation. And in many of the areas, the iron formation alternates with layers of black iron minerals like magnetite and red iron minerals that essentially are silica, a form of silica. And those are seen at a spot called Jasper Knob, west of Marquette, near Ishpeming. And that's just a magnificent outcrop with these alternating red and black layers. That's why we call them banded iron formation. And this turns out to be about 1.8 billion years old, these sediments. And they are essentially our main source of iron ore all over the world. There are similar iron-rich deposits in Labrador, in South Africa, in Brazil, and in Western Australia. And all of these were deposited at a time when the ocean had an unusual composition. Apparently, it didn't have that much oxygen in it. Otherwise, we wouldn't be able to dissolve the iron. And if the ocean didn't have that much oxygen, then probably the atmosphere didn't have much oxygen. And in fact, as you know, our early atmosphere was oxygen poor. And that allowed all kinds of peculiar things to happen in these sediments. Another thing that happened in these sediments is that the older continents to the north of the area we're talking about here, from the North Channel of Lake Huron all the way over to Minnesota. To the north of that was an older continent that had formed in the 3 billion year range, and it had veinlets of quartz type veins that had gold and uranium in them. Uranium is another element that doesn't like to move around if there's oxygen. But if there's no oxygen, you can erode off these pebbles. And so this stuff washed off into our 2 billion year old sea and formed deposits of uranium bearing conglomerates and sands. And these are what was mined at Elliott Lake in Ontario for many years, was one of the main sources of uranium ore for nuclear reactors. And this, again, is a signal that there must not have been that much oxygen in the atmosphere during this period of time.
Have those deposits been depleted?
There is currently no mining at Elliott Lake, and the deposits have been reclaimed. These sedimentary layers that contain those uranium bearing conglomerates and sands extend to greater depth in many parts of that region and could be mined again if there was a need for it. There are other sources of uranium that are currently being emphasized right now, so it's not likely that we'll go back to Elliott Lake anytime soon. There was also the possibility that those rocks might have extended into the Upper Peninsula of Michigan, and there was a fair amount of exploration 40 years ago, but didn't turn out to find anything particularly important.
So this might have been on the eastern end of Lake Superior.
Yes.
Yeah.
Now, in the eastern end, from Sault Ste. Marie eastward, in the Upper Peninsula, the rocks appropriate to contain those uranium conglomerates are buried beneath a 1 billion year old sedimentary layer. But that layer isn't so thick, and it was possible to explore through it and to look for these older rocks that might have been buried. So you could go up to Elliott Lake and you'd be able to go around and see some of these old conglomerates that contain uranium. There's a number of places that have been set aside. There's another thing that you could see in the region on the way to Elliott Lake over on the north shore of Lake Huron, and that's what's called the Galgandic tillite. And that's a rock, you'd recognize it immediately on the highway, particularly headed up toward Elliott Lake and in that immediate area, because it's a gray rock with great big pink cobbles in it. Quite a spectacular rock. And that rock resulted in part from a continent-wide glaciation that occurred at that time. It's a bit of a stretch to say continent-wide because we only see that in a few places in the world where rocks that old are exposed and are preserved. But where they are exposed and preserved, we find that. And so it suggests that whatever the size of the continent was, there was this significant glacial event on it. And this then would be the first time that there was a significant glaciation of the Earth. And as you know, the Earth has come in and out of these cold events several times in its history.
So how long ago would that first glaciation?
About 2.4, 2.3 billion years ago.
Oh, okay.
This package of sediments, it's a remarkable package of sediments. It's got some of the greatest iron-rich deposits in the world. It's got these glaciations, and it's got these strange uranium-bearing conglomerates. All of these strange things, all in one patch of rock.
That's wild.
Very special rock.
Huh. You mentioned
So
that these iron deposits that you referred to, are they still being actively mined?
Oh, yeah. Well, the Mesabi Range is a major source of iron ore. I've forgotten how many operations there are, maybe 5 mines on the Mesabi now. In the Marquette Iron Range, outside Marquette, there is one major mine operating and a second mine that is on standby. Both of these have extensive reserves. All of these mines do, and they are our resource of iron ore. If you're going to make a car, a refrigerator, or anything else, you can't have modern society without the iron ore that's supplied by these deposits.
Not to go too off topic, but so the iron that comes from these deposits, I mean, I don't know what the state of affairs is currently. Does this get exported overseas to the overseas steel manufacturers, or because I can't remember what the state of U.S. steel manufacturing is. I mean, I don't know if you're aware of
well, I can't give you an exact up to date on it, but the U.S. steel industry is essentially supplying domestic demand. The export industry for iron ore to make steel is basically Western Australia and the Carajás region of Brazil,
Okay.
which are supplying Japan and China and areas that are making much more proportionally iron and steel than we are. So
Right.
most of ours is Great Lakes. It's coming around the Great Lakes. It's coming through the Sioux and down to the bottom of Lake Michigan, where you've got the U.S. Steel operations, and then farther over into Lake Erie, and where their operations near Cleveland.
Hmm.
So it's mostly domestic consumption.
Yeah. Very
And
interesting.
so there's other stuff coming down from Labrador that's also going to those areas and to Canadian steel making ports uh, in the Great Lakes drainage basin.
Good. Thank you.
So I have a question. You mentioned this glaciation. Um, would that be connected with this snowball Earth event that happened back?
Well,
I think it was
Snowball
about.
Earth was around 600 million years.
Oh, okay.
And that's a much younger event, but it is a similar event. And a snowball Earth is a time when at least some people, not all, because there's controversy on this, feel that a much larger part of the Earth was covered by ice, not just whatever continents we had, but oceans, and to the extent that there was a real dearth of exposure of anything other than ice at the so-called snowball Earth time. Now, some people are extending that and suggesting that there was a snowball Earth event at the 2.4, 2.3 billion year time too, but we don't have that many rocks exposed around the Earth to verify that sort of thing. Even at 600 million years, it's impossible to verify it with rocks, and what you have to do is depend on what we call the modelers, who can take all of this information and model how the Earth would have behaved and how ice might have behaved under various conditions. So this is an area where there's a lot of activity, both in looking at the rocks and looking at the models, trying to decide. Of course, it's of great interest because we're not particularly interested in having the Earth go into another snowball event.
Right.
No.
At this time, is there a fossil record? Are there like sponges or stromatolites or anything from this era?
No, let's say yes and no. There's not much in the way of fossil material back this long because there wasn't much life. And of course, there's the question of when life developed. It probably developed way back billions of years ago, but very early on, if it developed, it might have been wiped out by meteorite impacts because there were very heavy meteorite bombardment in the first 500 million years or so of Earth history. So life might have come and gone. But you do see in the Banded Iron Formation in the Upper Peninsula, in the Marquette area, strange fossils, great long wormy kind of things that, they had to be a foot or two long. And you'll see those in the University of Michigan Natural History Museum. They're on display, and a number of places around the world. And those are 1.8 billion year old worm-like features that were found. And there aren't that many places where similar things like that are found. And it's true that at Jasper Knob, if you were to take the red bands or red layers at Jasper Knob and make what we call a thin section, where you cut it thin enough and polish it so you can hold it up to light and light comes through it, you'll see little life forms in there. There was stuff in the ocean at that time, but that's really the only place until less than 600 million years ago that we'd be able to show you any significant evidence of life anywhere in this region.
Good. Very interesting.
There was
Okay, so then where's our next I'm sorry.
well,
Where's our next stop?
I was going to say there's another place that we ought to mention.
Okay.
And that is that another big event happened at about 1.8 billion years ago. It was a nice day, and then it got all wiped out because a giant meteorite hit. Best estimates are that a meteorite, the third largest meteorite for which we have evidence today, there may well have been many other big ones, hit at Sudbury. And this thing threw out debris that is found as far west as Thunder Bay, Ontario. And of course, if you're going to find debris made by this meteorite, you're going to have to find rocks of the same age somewhere else. So, you can't go looking in Nebraska for the debris from the meteorite impact because there's no rocks of that age over in Nebraska. But there are rocks of the same age in Thunder Bay, Ontario, and I could walk you to a front yard in Thunder Bay that has no grass on it, and it is all rock, and it has chunks of rock this big that are disoriented and that were clearly thrown up into a pile by a tsunami. And the age of those rocks is known for various reasons. And similar rocks are exposed west of Marquette. I couldn't direct you to the outcrop. There's only one really good outcrop because it's such an esoteric location. And if you got there, you'd shrug your shoulders and you'd say, why'd I come here? Because it's not that spectacular a rock. But if you want to go to Thunder Bay, just cast around, and there are plenty of field trip guidebooks that locate these outcrops. Also, the Gunflint Trail in Minnesota has several outcrops that show this. And this outcrop of the meteorite impact pretty much ended the sedimentation of Banded Iron Formation. You had one day when you were making the Banded Iron Formation, you had this strange iron-rich ocean. And the next day you have a meteorite. Well, you can imagine the meteorite would have mixed things up a little bit. And one proposal has been that the reason we stopped depositing these iron-rich sediments is that the ocean was mixed by the Sudbury meteorite. That's a thought, and it's the kind of thing we throw out in geology and we work on trying to evaluate.
When you say mixed, in what sense? Like the introduction of oxygen or something, or what does that mean, mixed?
Well, I mean, we would have sloshed so much rock around that, here's the thing I should point out. The ocean might well have been stratified. The deeper part of the ocean might have been oxygen poor. The upper part might have had some oxygen in it. If the deeper part was oxygen poor, it could have contained dissolved iron, and that could have been washing up on the shallow part to make these iron formations. Well, if you splash a meteorite in there, you're going to destroy that stratification. You're going to have a well-mixed ocean, and it's going to stop depositing its iron because the iron is just going to slosh right out of solution onto the ocean floor. And of course, the ocean floors are subducting. Remember, we're going to have plate tectonics, and they're going to go back into the mantle, and they won't be preserved, and we won't see them.
Okay.
So the oxygen that was around at this time, I think we're talking. Did you say, are we at 1.5 billion or 2.5 billion?
Well,
I forgot.
The Earth
would that be the
Earth is never that simple.
Yeah, I know.
all of the evidence that has accumulated over the last 2 decades, 3 decades, shows that the oxygen content of pre 2.5 billion year rocks was low of the Earth.
Yes.
Post 2.4 or so, there appears to have been an increase. Now, you'd think, okay, all the iron that's dissolved in the ocean should have been deposited out at 2.4. But we can go up to the Upper Peninsula and we find the Mesabi and the Marquette Range. We find all sorts of uranium conglomerates. We find all of this stuff that is younger than 2.4 that is telling us that the oxygen didn't get that high. It may have gone up, but it didn't get high enough to stop these processes. And in particular, the iron formation, probably depended on some sort of a stratified situation where you might have had oxygen in the atmosphere, but it didn't get in and totally mix the ocean until much later, possibly 1.8 billion years ago. It'd be much simpler if those iron formations were around 2.4 billion years old, but unfortunately they're not.
Mm-hmm.
And actually pinning down their age was a big achievement only about 20 years ago, 30 years ago, by some of the U.S. Geological Survey scientists working in the area.
What kind of like what technique are you referring to? I mean, we're not talking carbon-14 dating or
No,
this is
zircon. What they're doing is first they have to do detailed mapping.
Mhm.
They find the distribution of these iron formations, and what they have found is that they interfinger with lava flows. So here was iron formation, and a lava flowed in on top of it, and a little more iron formation on top. And so they know that the lava flow was coeval, we would use that term, with the iron formation. And so the lava flows can be dated, to use the term. We'll measure their isotopic age by looking at minerals and using mostly uranium lead.
Mm.
That gives us then the age of the iron formation from the age of the lava flows.
Very interesting.
So
and
that
the lava flow. I'm sorry.
No, go ahead.
I was going to say, and the lava flows were from the rifting, or is this before the rifting time?
That's before the rifting. We haven't done any rifting yet. What's happening in those lava flows? Well, I shouldn't say that. Oh, it's getting complicated.
Yeah.
You see, we made this continent at 2 point, starting at 3, 4, and we were making a continent all over this area. And at about 2.5, it did break apart. And we don't know where the stuff on the south end went. It might have gone to Australia, and it might be showing up now in Western Australia or in South Africa. But when you rifted it, you had a continental margin much like the eastern United States, where you had a submerged continent underneath an ocean, shallow water, and that's where all these sediments that I've been talking to you about were deposited. Okay. Well, once in a while, some lavas would have come up from that rifted continental margin and flowed up into these sediments. But all of that is long before the so-called mid-continent rift.
Yeah.
Very interesting.
Well, there's one more event. It just kept coming at us. Something came back. We had a perfectly good continent working there. We had a continental margin. We were making all these beautiful sediments on that continental margin. The meteorite came in and hit at about 1.8. And almost the next day, an arc of islands, similar to what we see in the Aleutians today, a long chain of volcanic islands, came chugging up from the south and ran into the south end of the continent with all those sediments and mushed them all up and made a giant mountain range. And that was the so-called Pinocchian orogeny. And that actually happened over a rather extended period of time, possibly several 100 million years. And it built the only really good ski hills that Michigan has ever had, with all due respect to the ones up around Traverse City. And it made very big mountains similar to what are the Himalayas or today. And those mountains were so big, in fact, that, like the Himalayas today, the tops of them slid off. Because, there's a limit to how high a mountain can go because of the strength of the rock. And the rock essentially loses its strength. There's fractures in the rock and the top part slides off. Well, when the top part slides off, you got all that hot stuff down underneath. And it's not molten. It's just hot rock, but it oozes like a plastic, and it comes up and makes fantastic convoluted shapes. And those are best seen over in Georgian Bay.
Hmm.
And as a tourist going around the area, you'll see all sorts of pictures of the incredible contorted, convoluted rocks that are exposed up around Parry Sound and Georgian Bay. And that is essentially the bottom of this mountain range that oozed up when the top slid off.
Hmm.
So
So now you're saying, just so I heard you right, you're saying like the mountains that exist in northern Michigan beyond, those were triggered by this Sudbury comet impact?
no, no, and in fact, I need to correct myself. That stuff over in Georgian Bay is younger. I've equated it with the wrong event. Um, let's see. First of all, the Sudbury meteorite came in and mixed up the ocean, and shortly thereafter, these collision events began to occur
I see.
in which we pushed the sediment up and contorted the sediment and the underlying basement rock, the older Precambrian rock. And where you can see that, and that rock then, that mountain range did, the top slid off, and the hot bottom rock came up and oozed around. And best place to see that is Republic, Michigan, where if you look at a geologic map of the Republic area, you see that there's an iron formation that goes along just perfectly traceable for 20 or 30 kilometers, but on the surface, it's just like the old rock around it oozed up and lifted it up, and then it was eroded off. So you see this little keel of folded iron formation that should have been flat, but it's not. It's all folded because the stuff that it was deposited on, this old 3 billion year rock, oozed up. I'm sorry, this gets really complicated.
I can see.
It's interesting, though.
It's hard to visualize it, but listen, if it's hard for me to explain it, imagine how hard it is and how hard it has been to try to decipher it.
Yeah.
People have had to map it, people have had to measure ages. The ages come up different from what you thought. You go back, you map it again, you come back, you make some more measurements, and that work is still going on. But the basic bottom line is that after about 1.8 billion years ago, we had finished making a mountain. We had begun to erode it off. It had slid down. We'd eroded it off. And somewhere in there after 1.8, maybe 1.6, 1.5, we had a flat continent. And it just sat around there doing nothing terribly exciting until about 1 billion years ago.
So what were the name of these mountains? Do we have a name for these early?
Those are the Pinocchian Mountains.
Pinocchian Mountains. Okay.
Yes, and there's no place you can go and stand on the Pinocchian Mountains because they have been eroded down to essentially flatness of the Upper Peninsula. Just imagine in a few 100 million years ago or in the future when the Appalachians will have been eroded down to flat roots. It's that sort of thing.
Right. Okay.
So could you remind me where Republic, Michigan is? I'm not sure if I remember.
What? You don't know where Republic is an active little town. It was based on the Republic Iron Mine, which is you would drive west from Marquette. I can't remember my distances, but tens of miles, and you'd turn south and drive maybe 20 miles, 15, 20 miles south to Republic. It's maybe 30 miles west of Marquette, but it is a continuation of the same iron formations that are mined in the Marquette area.
Okay, so are we ready to move to the next
our next stop.
Next tourist attraction?
Well, that's the Mid-Continent Rift.
Okay.
And
The infamous Mid-Continent Rift.
yeah, it was one time when North America tried to rip apart. Now, we've already said that it ripped apart at one point here at about 2.5 billion years ago in order to make the sediments that we just talked about. And the piece of continent that ripped off there went somewhere and we don't know where.
The rift at 1 billion years is not really connected to the one at, say, 2.5 billion, right? Or, I mean, it's not because there was a weak spot in the crust and somehow it reappeared. Is that a correct statement or not?
Yeah.
Are they related in some way?
No, I think in general, actually, our overall story is we should back up just a little bit. That during the formation of the Pinokian mountain range, in addition to that volcanic island I mentioned, there was a very old continent. In fact, it's those nearly 4 billion year old rocks that we see here and there and in the Minnesota River Valley. Well, that was another continent, and that came in and mushed up against the rocks to the north. And so at 1.8, what we had was an ancient, almost 4 billion year old continent that had come up against these volcanic rocks and that were about 2.5 billion years old. And to the north, we had another old continent that I mentioned that's exposed in Marquette. So we had this kind of composite continent. And we built the Pinokian Mountains out of those collisions, and it had then been eroded off, and it was flat, and it was minding its own business. And at about 1.1 billion years, a very hot part of the mantle began to rise, the mantle being the layer of the earth that's underneath the crust. And it came up, and we call these mantle plumes. It was very hot rock that rose, and the form of a plume, it would be to rise like this and to spread out. And that action then causes the continent to be bowed up in the center. And by observations that have been made in many areas, it can be seen that when the continent bows up like this, it usually splits in three places, sort of a 1, a 2, and a 3, and equally angularly spaced around the center. And if the bowing up continues, then those three pieces tend to move away from each other. Well, usually two of those splits take over, and the third one fails. It's called a failed arm. And what we had was that sort of event happening under the Lake Superior region. And the two arms that succeeded are the ones that go down from the center of Lake Superior down through Duluth, all the way down through Minnesota and Iowa into Kansas and Nebraska. And the other arm came out of central part of Lake Superior, went around through the Sioux and right down through the middle of Michigan. And we don't know exactly where it went after that because it got down to southern Michigan and it's cut off by later younger rocks that I'll mention in a minute. The failed arm is Lake Nipissing, which is immediately north of Lake Superior, central Lake Superior. And the failed arm had some activity, geologic activity related to this event in it, but the real activity happened in the two active arms, and an enormous amount of lava came flowing out. The thickness of lava that accumulated is just amazing. It's 20 to 25 kilometers of flow upon flow upon flow upon flow. And these were big flows in some cases. The Greenstone flow, which is the largest one known, is up to 400 feet thick and extends for tens of miles in length. Now, these were very fluid lavas, and they were so fluid that there's no way on Earth that one of those things could have piled up and been flowing along 400 feet thick. But what you can have is a situation where it comes out and it quenches on top and kind of makes a carapace that begins to inflate. And if you keep that going, you can make an unusually thick lava flow. And that is exposed right through the central ridge of the Keweenaw Peninsula. And if you've ever hiked Isle Royale, the entire central ridge of Isle Royale is this lava flow. That's the greenstone flow. And in Isle Royale, you can look at the tilt on that flow, and it's tilted southward into Lake Superior. And if you go around to the other side of Lake Superior in the Keweenaw, there it is, again, tilted northward, where it's the continuation of that flow. And if you look at that lava flow, as you can do anywhere in that region, you'll see little bubbles, little holes, and those holes are from the gases that were dissolved in that lava, expanding and being quenched and giving you what we call vesicles. And those vesicles, of course, allowed water and everything else to flow through that rock after it's solidified. That turned out to be kind of important.
Is that like a pumice looking type of rock?
No, this is a pretty heavy rock. If you were going to use the term, there is a term scoria, which is not quite appropriate. But no, this rock would definitely be quite heavy. These rocks were basalt, very similar to what we see in Hawaii in most places. Pumice would be found would be a rock of a different composition that forms under a different conditions, and it has much more silica, and it's so much more viscous that when the bubbles come out, they can't escape, and you get so much more bubbles in the rock that the rock actually has a low density and will float.
Yeah.
You're not going to be able to float any of these rocks. The bubbles came out and they got out, and the rock will sink like a stone.
If I was hiking in this region that you're referring to, would I kind of need to have an expert guide like yourself to know what I'm looking at, or could they be? Are they unique enough? Are they easy to identify? I guess once you have like a checklist of things to look for.
Well, I mean, here, the best place to see the rocks of the Mid-Continent Rift are the Keweenaw Peninsula, and almost anywhere you stop the car and there's rock, you're going to see lava flows. But the best place to see them is Hunter's Point, which is up near Copper Harbor, and that's a little state park, and the trail goes around to a nose sort of along Hunter's Point there, and you can walk along and you can see the lavas stacked one on the other, and you can also see sitting on top of the lavas the Copper Harbor conglomerate, and that is a sedimentary rock consisting of cobbles of volcanic rock. And so in addition to the volcanic rock that makes up the Mid-Continent Ridge or Rift, we've got sediments that washed off of the lavas after the lava flows stopped coming in. You had mountains of lava around, and that washed off and was collected in these sedimentary rocks. So you can see both. They're very clearly exposed, and you can see the contact between them. And it's an excellent place to really get a feeling for what it looked like. And if you want to see on a larger scale what it looks like, you can go to Copper Harbor and take the little road that grows up toward Brockway Mountain. And what do they call it? There's a scenic drive that goes sort of along the ridge right there. And particularly the view north from a couple of hairpin turns in that area, you'd be looking north up the Keweenaw, and you can see that the lay of the land is just dipping northward. And what you're looking at is the individual layers of lavas that are all dipping northward under the lake. and going to come back up in Isle Royale and other areas to the north. Now, I should point out that the reason that they sagged like that is because the mid-continent rift did not go to completion. It didn't rip the continent apart. It just made a big crack in it. And we'll get to why it might have stopped in just a minute. But when it stopped, the rock cooled. And when the rock cooled, it contracted and it sank into the mantle. And as a result, what was originally an uplifted, up-bowed region became a down-bowed region. And it collected sediment like the Copper Harbor conglomerate, the Jacobsville sandstone, and younger sediments that came in at about that time. I should mention the Jacobsville. It's a red sandstone, very, very, very distinctive. And Jacobsville is a little town on the southwest corner of the Keweenaw Peninsula, southeast corner of the Keweenaw Peninsula. And that sandstone was mined around Jacobsville and sent all over the place. So whenever you're driving around the area and you see a reddish, not rust color, a more rich red color, purplish red, you'll be looking at Jacobsville sandstone, which is a 1 billion year old sediment, the last one to wash in and fill the bowed down area that formed when the mid-continent rift sagged down.
So when I've driven around Marquette, I noticed there's the soil along the road sometimes looks reddish. Is that sandstone? Or is that from the iron?
No, in some areas it'd be more to the north. If you in some places, yes.
Yeah, I see.
Another place you can see it is up at Presque Isle Park, because right there you have the Jacobsville sitting right on top of the older rocks, and so it's the sandstone that caps Presque Isle Park.
I see. Okay,
it's interesting. I'm just looking at a map. Jacobsville, Michigan, is technically a ghost town.
Yeah.
So I mean that'd be a great vacation. You go there to check out a ghost town and see all of this interesting geology all in one trip.
Well, if you look around there are some old pits, old mines, and they took the Jacobsville out in blocks because it was being sent around as building blocks. And you can find some of these old pits. They are remarkably hard to find because they're so overgrown, and they were relatively small, but they're right along the shore. And if you look at Google Earth images, you can see them, and you can see where the old spits were that they used to load the rock onto the ships. You can see the remains of those. The Keweenaw is famous because it was a major copper mining region in the late 1800s and all up until the mid 1900s. And the copper ores there were deposited by waters that flowed up from the hot bottom of the rift, and the waters had copper dissolved in them. And as the waters got near the edge of the rift, they precipitated copper and other minerals in these holes. And sometimes you can see cracks in the rock. They would have filled cracks. And sometimes they formed very large masses of copper. And it's very important to recognize about these copper deposits in the Upper Peninsula that they were what we call native copper. That is copper metal. And copper usually in nature combines with sulfur to make copper sulfide minerals. Those have to be smelted by a process that drives the copper off to get copper. But these copper deposits were pure copper, and they required less refining to be used. And so mining of these things proceeded for decades and was the major supplier. I have been told, and I can't verify it, that one of the reasons that we're on Eastern time in the most of the Upper Peninsula is that the moneyed elements in New York that owned the copper mines wanted to know what was happening in their copper mines at the same time that they were. But at
Right.
any rate, this copper still exists. It's been mined down underneath Lake Superior, and
Yep.
gradually you get to a point where the copper quality, the amount of copper in the rock, diminishes. But you also get to a point where the cost of mining it, because of the distance you've got to go underground, exceeds the value of what you're extracting. So there is still a lot of copper in the Keweenaw. There's another kind of copper deposit related to this, and this is the white pine deposit. I won't bother you with the distinction because white pine and the Keweenaw deposits all formed by essentially the same process. And the white pine deposit has also been mined out in large part, but not entirely, and that's over near Ontonagon.
Mm.
And there is an area of the white pine ore just west of Ontonagon that is eligible for mining now and has been permitted and might be mined in the future. But these are important resources. We need electricity in order to get away to have electric vehicles and everything else. And they use enormous amounts of copper. So we have to find copper in order to supply them.
Well,
Yeah.
I think about 10 years ago visited the Quincy mine in Hancock, Michigan, which
Yeah.
which was and it had, I think, 90 levels that they dug at a like a 60-degree angle that followed that copper vein under the lake. But it was all but 4 levels were filled with water. And they said that one of the reasons that that the mining became difficult is because the copper is so pure that it's like drilling into paste, and it's much easier for them to go out west and, do an open pit mine and just gather all the rock and process it there than trying to get out the pure copper in the veins. Is that your understanding of anything like that? Is it your understanding of what happened to the copper mining?
Right. It's actually a rather strange situation. First of all, your levels, because you've got this mine that's going down on this horizon, and it's mining a level, and so it stops at 100 feet, and out go some what we call drifts. You'd call them tunnels, and they mine that. They go down another 100 feet, so those levels would be drifts that extended out from the inclined shaft.
Mm-hmm.
But you're right. I mean, what are you going to do? Just imagine yourself digging a drift or tunnel, and you come upon a face in your tunnel that might measure 8 feet by 8 feet, and it's pure copper. You're rich, right? Well, exactly how are you going to get it out? You fill a hole in it, you're going to blast it, and it just goes boom, and nothing happens. And so one of the things that I have been told, I wasn't there to see it, was that they would take the older miners down who couldn't do the heavy work, and they'd give them a chisel, and they'd chisel off the copper, and you'd get fingers of native copper that come into a sort of a hand form, bigger than that, and they call them fans. And those fans are, of course, real items for collectors to find today. But most of the ore that would have come out would have been little blebs of copper in an otherwise rock that breaks fairly easily. So when you bring that up to the top of the surface, you can crush it. But if you crush it by normal means, which would be a machine that does this, essentially what you do is just smear it around. But if you take what's called a stamp mill and you whack it with extreme force, extremely rapidly, you shatter the rock and you separate the bleb of copper from the shattered rock.
Mhm.
And that's how it was processed. And the rock, waste rock from that then, called tailings, was piled up in many areas in the Upper Peninsula. It contains some copper, but also mercury. And those tailings turn out to be an environmental problem because people really didn't think about it back in the old days. They didn't realize how serious it would be. Not only are those tailings releasing mercury, but they are also washing along as sands, and they're coming in and covering otherwise good fishery areas, particularly down at the lower end of the peninsula, and contaminating them. So this is a legacy issue that we are dealing with in the in the Keweenaw. And I hasten to add that modern mining wouldn't do anything like that. But in the 1800s, people weren't thinking about it, or if they weren't paying attention to it.
Is this what you're there's this White Pine North project? It seems like this is recent. And it looks like this is I mean, I was just reading through the feasibility study and first quantum minerals, and then yeah, this has got to be what you're referring to.
Well, this is the White Pine area, but what I'm referring to is piles of tailings that are offshore. Around the White Pine area, there are both mining tailings and tailings resulting from smelting, because the White Pine ore was copper sulfide, and it didn't behave quite in the same way.
It seems that mining today would be so fraught with regulations. I mean, rightly so, like all of the ESG, expectations. I mean, my guess is that they've gotten a lot smarter, than blowing up mountains and or the old ways.
Well, yeah, I mean, people have gotten a lot smarter. I mean, we've got a problem here. We all want copper, but we want it to be available at the hardware store, and we don't want to look at how the sausage was made. We just want it to be there. And what we have to do is recognize as a society that we have enormous challenges in getting these things from the earth. And that, of course, we can't recycle and get everything we need because demand is increasing. You can't recycle everything you use. So there's no question we have to mine new material. It's essential. Well, if you're going to do that, where better to do it? Shall we do it in a developing country where the regulations are poor and we are going to hurt areas and hurt people perhaps? Or should we do it in a developed country where the regulations are more rigorous, where the knowledge is better, and perhaps where the money is available to do it right? And I think as responsible citizens, the answer is, if we put we never got a woman up there on the moon, surely we can dig out what we need out of the earth without it becoming impossible. Because if it is impossible, of course, then what we're saying is we're going back to the Stone Age. So we've got to find a way to do it and satisfy everyone. And our challenge in that, in many cases, is many people don't have any real sense of how the earth works. For instance, they'll use the term pristine very widely. And I can take you to many places that people would call pristine that are naturally polluted, that would in fact kill you if you drank the water, but it's nature doing it. So the world out there to begin with isn't very pristine. And secondly, the other thing people don't have a good feeling for is just how wide an effect something might have. Indeed, if you have a mine and it drains down a stream, it can pollute that stream and perhaps immediately adjacent areas, although it shouldn't, because it should be operated in a way that doesn't do it, but accidents happen. But it's not going to pollute the entire Upper Peninsula. And so the scale of things is something that we all need to get a better feeling for. And I have to say that our state agencies are very good about that. They have a good feeling for the scale of things, for the importance of things, and the degree to which they are environmentally important. We have regulations that are overwhelmingly complex, but our agencies help you through those regulations. And so far, we have done an excellent job of permitting mining and continuing to exploit our resources responsibly without saying, oh, we're not going to do it. Now, I'll take you over to Wisconsin, where in many parts of Wisconsin, the citizenry just says, nope, can't do it. And as a result, there are some significant mineral resources over in Wisconsin that have never been developed, that remain in the ground.
Would this be in the northern part of Wisconsin?
Yeah.
Sort of on the Michigan-Wisconsin border?
Well, all the way from the border, all the way over toward the Minnesota line. But you could ask, okay, Wisconsin people, if you're not going to join in the challenge of getting this out of the ground in a responsible way, should we give you any that we got out?
Right. Yeah. It's like water wars.
We're all going to have to get in this together. We got a challenge here, and it requires an informed public and a thoughtful public to do it right.
Is there a tension between state and federal? Are there federal mining lands that are pretty widespread? Or it's, to me, that's really interesting to hear you talk about just the difference in jurisdictions, how Michigan is markedly different from Wisconsin. I thought there'd be a lot more uniformity, and I guess it's a good thing there is not, but curious about your take on that, and again, the role of the federal government.
Well, we're talking really about two things: land access and then production or land use. And the Upper Peninsula of Michigan, large parts of it are controlled by the state parks, state forests, the feds, federal parks, federal land, federal forests,
yeah,
and by large private landowners, timber companies. So that's where most of the land is controlled. And so access to that land would be controlled in large part by the owner of the land. Sometimes, of course, the ownership of the surface and the ownership of the minerals, so-called mineral rights, are severed, and different parties could hold different rights. But where I'm going with this is that is talking about access to the land to see if it has anything on it. And that requires exploration, which is a very costly process that usually fails. Huge amounts of money are spent looking for stuff that's never found. Once something is found and it might be mined, then most of the regulations that you would have to deal with in terms of permitting are at the state level and at the local level. So there's where the distinction is. And so different states have different approaches to permitting of mining activity or any sort of activity.
I see. Yeah.
So do you think it would ever be possible again to, say, open the Quincy mine or something nearby and feasibly mine the copper? I mean, like what would the price of copper have to go up to in order to make that a economically viable thing to do? Is that a loaded question?
But I can tell you that 200 years from now, we're going to need a heck of a lot of copper, and we might well be back in there. or maybe 100 years from now. I doubt we'll be back in there 10 years from now, but there are areas in the Keweenaw, the Copperwood area that I mentioned, the extension of the White Pine, that are currently permitted for and might be mined. Price of copper right now is $3.80 a pound, roughly. If we got copper to $4, $4.50, it might be feasible to mine copperwood. But my guess is just, we need $8 copper. We need $10 copper. Give me $10 copper, and they'll be mining all over the Keweenaw. But it's not tomorrow. Think hundreds of years into the future, we're going to continue to need that stuff, and we're going to have to find it somewhere.
We hope you have enjoyed our discussion with Professor Kesler. What we have tried to do here is inform people of the immensity of geologic time that is still preserved in places like the Upper Peninsula of Michigan. So if you travel to Marquette, Michigan, for example, you can stand on the shore of Lake Superior, south of town, and view the Pillow Rocks, whose age reaches back over 2 billion years. Also, the listener should have some understanding now of how and where all the iron ore and copper ore in the Upper Peninsula formed. These processes reach from the deep past, where the earth was a very different place, to the present, where their mining has greatly affected the life and economy of the region. We would like to thank Professor Kesler again for appearing on this podcast, and we hope that sometime in the future we might get Professor Kesler to come back and to discuss another very important topic to our region, the glacial formation of the Great Lakes themselves.
Sweet Mother Michigan, Father Superior, coming down from Mackinac and Sault Ste. Marie. Blue water Huron rolls down to Lake Erie, falls into Ontario and runs on out